Welcome everybody, good afternoon. So this is 719 Mathematical Economics. And today we're gonna work on optimal control theory. We're gonna start working on optimal control theory. Let me share my screen now and with a empty page. Okay. So this is optimal control theory. Okay. And the idea is this. So up to this point, we studied a problem like this, right? So we had a problem like this, right? And then we also studied dynamical systems, okay? Where possibly this was given, okay? Now what we want to do is to make this model dynamic, make this optimization problem a dynamic model, and then study not just optimal points, okay, but optimal paths, okay? So these paths will change in time, okay? In optimal control theory, usually we start with this specific example, okay? In some textbook, it is called the cake eating problem, okay? So obviously, there is this nice cake, okay? You can actually have candles in it, all right? So this is a cake. And suppose that there are 8 slides, okay? And your utility your utility depends on consumption of cake, number of slides, okay? And T is time, obviously. Now the idea is that you just want to maximize utility, not just for today, but for some horizon, okay? Now suppose that time is continuous, all right? And you want to maximize your utility from the consumption of this nice cake for, let's say, this interval, okay? So how do you define it? Okay, how do you define it? Well, since time is continuous, you can define it in simply this way, right? So for each instant, you can eat this cake, right? For each instant, you can talk about consumption, and then that consumption will give you some utility again for each date, right? Then you add all these utility levels, all right? So then your objective function could be, let me switch colors. Let's say your objective function could be this, okay? And obviously you are choosing CT. Okay. Now let's imagine the constraints here. Okay, now first of all, consumption cannot be negative, so you have the familiar non-negativity constraint, right? But then you must have some other constraint, right? First of all, you have 8 slides. Now, how do you now write a constraint that adequately describes this story? So obviously, if you think about it, the total amount of slides should be larger than your total consumption, right? How do you express your total consumption? Well, your total consumption in this interval would be something like this, right? So you clearly now defined the problem. Now, what you are looking for here is not consumption as a single number, but instead, you want to find this. This is time, this is 2, this is 0, and this is CT. You want to find this function, okay? And this path must be optimal, okay? That's the example. But there is a problem here, a couple of problems. One problem is that according to this formulation, the consumer does not really differentiate between different time episodes, different periods, right? According to this formulation, time 0, compare these 3 dates: t equal 1, t equal 0, t equal 1, t equal 2. Okay? So you have UC0 here, UC1 here, and UC2 here. So obviously, all of these utility levels have the same weight, right? In other words, if this is your utility function, the marginal utility of C0 equals marginal utility of C1, which is equal to marginal utility of C2, right? Now, is this realistic? Think about it. In an economy like this, or in the real world, do you actually put equal weight for different time periods when you take a decision like this, right? Because this decision problem, as you will see in a couple of minutes, is actually a dynamic resource allocation problem, right? There is this resource, the cake, and I want to allocate this resource to some purpose in different periods, right? Now, in such a problem, it is much more realistic to describe this consumer here as an impatient person, okay? Impatience. So in general, we call this notion time preference, okay? And usually we imagine something like this. Okay? Now, what you see here is a bit, very similar, but there is this term. Okay? There is this term, and this term is called discounting term. Okay? And it depends on what we call the discount rate or subjective discount rate, because it is subjective because it's part of the preferences of the agent. So you may imagine two different people that have different levels of time preferences, different levels of discount rate. Okay. Now, what does this discount rate do? Think about it. Rho is some positive number, right? Then at t equals 0, which is your initial period, initial instant, at t equals 0, this guy is equal to 1. All right? And for t greater than 0, it is less than 1. Right? For t converging to positive infinity, this converges to 0. Right? So what's going on here? Well, today, I have no discounting, right? Because today is today. When I eat one slice today, then I have U1. Okay, I don't since it is the present time, I have no discounting. But in the future, 2 days later, the same cake, the same number of slices, will not give me the same utility. Why? Because I'm impatient, because I want to consume, ideally, all of the cake in future, in present, right? So when time passes, I decrease the weight I attach to this date's utility. Okay? And of course, when t goes to positive infinity, I don't really care. Right? I attached, when t approaches infinity, I attached nearly 0 weight to that extremely distant future utility flow. All right? Now, why this particular exponential form? Do you have any ideas? Well, it is because of the compound interest rate, right? Because if this is a monetary problem, if this was a monetary problem, and I will show you in a moment how this can be translated into a monetary problem. If this was a monetary problem, then the resource, the cake, or my wealth, let's say, my stock of assets, if I do not consume them, I can put them into a bank account for some interest income. Now, in that type of understanding of this, interest income notion, you will realize that if you do not, if you let this money accumulate itself in a savings account, then your wealth accumulation process is subject to this exponential growth formula, right? Because if you do not interfere with that accumulation process, if the capital always there, and if the new interest income becomes the part of the principal, let's say, then the compound interest formula says that your wealth accumulates at a particular rate in an exponential manner. Okay. For this reason, this is typical in the analysis of discounting. All right. And you may also imagine, of course, to understand the full meaning of discounting, you may imagine the firm problem. Okay. Now, suppose that there is this firm. Obviously, the value of a firm, okay, is the present value or the discounted sum of future profits, and this discounting, if this is in real terms, must be done at the market interest rate, right? If you take any finance lessons before, this is the simple formula, simplistic one version actually, formula of the value of a firm. So if you want to buy a firm, in the stock market, let's say, or if you go to the owner and say, okay, I want to buy your firm, then the price, you should be paying is about this, right? It's about, so you wouldn't pay, a total amount larger than this present value at time zero, because again, the total market value of a firm is equal to this, right? So in other words, what I am using is this. So this is the current value. Let me use a different page. So this is for this horizon. I take any t, okay, any t, and I have this utility flow. I have the consumption, then I have the utility flow. Now this is the current value of UCT at t, right? At this particular t. Now this one is the present value of UCT of t at 0. Okay? So I'm interested, of course, in the present value of stuff. Why? Because I'm taking my decision here in the present. I'm gonna describe my problem of finding a dynamic path, but I'm gonna solve this problem today, and then I'm gonna execute the plan. All right? Now, if you compare this to this, this one is more realistic in the sense that people are impatient and they want to consume today. Otherwise, if they are not consuming something, and if they're accumulating something, then this must bring them some additional value from somewhere. Okay? So that's the notion. So that was the first thing about that problem. Now, recall that we expressed the problem in this way. Maximize from 0 to 2 UCT dt by choosing CT subject to this and this. Okay. Now, there's a practical problem here, because it is difficult to solve this problem. Why? Because there is no state variable. I mean, there's a state variable here. This is the total amount of cake. If you do not denote this by S, you have S0, right? S0 is 8. But now what you want to do is to understand, how does S change in time? How does S change in time? In other words, you may want to formally define this. All right? Now, how do we do that for this problem? Let's say I'm at t equals 0. I have S0 and I consume C0, right? Now, what happens in the beginning of t equal 1? If time was discrete, I would have something like this, right? So then I can actually write this for continuous time, right? For all t in this interval, I can actually have S dot t equals S0 minus CT. Okay? Now, instead of this, I can actually work with this one. So I can write my problem finally in this way, right? Maximize from 0 to 2 where rho is positive. I'm choosing consumption. Subject to consumption must be non-negative. This is true for all t, obviously. And then my state variable should follow this equation for all t again. And I know my initial state. Okay. So then I understand, okay, when I take a decision, okay, that decision, given the current state, will determine how my state changes from one instant to another. All right? So why is that important? Because in the next instant, when I'm going to choose Ct plus delta t, right, where delta t is a very small amount of time, then I'm going to look at what happened to my state. So I'm going to look at this. Okay? Right? So this is much more simple to solve this, much more simpler to solve this problem. That's the idea that we're going to exploit. Okay? And one last thing, obviously, in most of the time, we're going to work on infinite horizon problems. Okay? There are, of course, finite horizon problems. I'm going to show you a couple of examples there next week or possibly the week after that. But in general, we're going to look at the infinite horizon problems. Okay? So any questions so far? You get the sense of the, you get the sense that this is highly, strictly economic, right? Because you have resources, those resources will change in time depending on your current choices. Then in the future, you're gonna face the results of your earlier choices, so that what you want to do is to take this all into account and create one optimal plan in the beginning of time. All right? And if you are successful in that, then you're going to execute this plan, and your utility or your profit or whatever you are maximizing or minimizing will be achieved. Okay. Any questions, comments, etc.?
Can I ask a question?
Yeah, of course. Go ahead. Who are you? Yalçıner? Is that you?
Yeah.
All right. Go ahead.
About the discount rate, it changes with respect to the problem, right?
Well, of course. I mean, it changes depending on how you define your agents. You may, for instance, you may do that. There are two countries. You want to understand the growth processes of two countries, how they accumulate capital, for instance. You may want to assume that one country has a larger discount rate, another country has a lower discount rate. Or you may imagine two consumers. One type of consumer has high discount rate consumer, the other is low discount rate consumer. You can actually do this. There are papers like this. You may imagine that people, when they have kids, they invest in the behavior of their kids. So if they want the kids to be more impatient or more patient, they invest in that. So it can actually change in time as well. So in general, we write something like this. This is not very typical in mainstream econ, but especially in some environment problems, we sometimes write this. Okay, so this is again the same. You have some utility, and then there is this discounting term. Let me use another letter. So there is this discounting term, and again, you change the time. Now this discounting term will be in general some function of t, right? And typically we imagine that it is a decreasing function of t. But there are different types of discounting. What I showed you is the simplest one that is, that is much more common in the literature. But there's, for instance, something called gamma discounting. You may check the work of Weitzman. In terms of environmental catastrophic models, gamma discounting is important. Much more generally, some people, so that's a philosophical issue, right? If you make this model an intergenerational model, okay, suppose that this is an intergenerational model. So today you are living at t, that's yourself. At t plus 1, it is your children. At t plus 2, it is your grandchildren. Okay, now you may ask, is it ethical to discount the future? All right, so these are interesting dimensions, but in most of the literature and in most of the applied problems, we see that this is exponential, and in a discrete time framework, I will show you that when time is discrete, it goes like this. T can go to positive infinity as well. If time is discrete, that discounting term would be equivalent with this type of discounting, okay, when delta is between 0 and 1. Why is that form? Because in discrete time, if you look at these two formulas, okay, let's say this is discrete time and this is continuous time, the pace of decrease is the same, okay? How same? If delta is equal to 1 over 1 plus rho, okay, because 1 plus rho becomes the gross rate. I will show you the proof when we go into the discrete time problem, but this is one type of discounting that we use particularly, and it's particularly common in a large portion of the literature. That's the reason we are using that.
Thank you very much.
You're welcome. Anything else? Okay, then my time is 1:35. Let's take a break now and meet at 1:50. All right. Is that okay for everybody?
Yes, okay.
Yes, okay.
All right, good enough. Okay, let's meet at 1:50.